to this YouTube video and series of solving LeetCode questions. So today we are going to tackle question number 50, which is a LeetCode power of x and n, and the idea is to replicate the power function. And for those of you who are new to this series or to this channel, first of all, you're welcome and thank you for watching. This series is not an absolute tutorial, but more of a realistic point of view on how a software engineer solves questions on LeetCode. So today we are going to be doing a medium one. As you can see, I already solved this one. I solved this one some few minutes ago, about 30 minutes ago. The problem was I never had an idea on how to do it, so I had to do some research. And so this video, apart from this one, the past videos I've been doing realistic solving, where I get the question, I don't solve it. If you check it, you see it. But for this one, I thought normally I would skip this video and go to the next one and solve some other thing and then record myself solving it. But I thought to myself, you know what, this was very interesting, and these are the problems these are the kind of problems that if you don't see them for the first time, you're going to face difficulty solving them efficiently. And so I thought, let me just revisit this question while I make a video on it and solve it. It's also going to help me practice and understand it more, and hopefully we all get better by doing this. So let's dive right in. The question reads: implement power x of n, x and n, right, which calculate x raised to the power n, that is x to the n. And you have examples. As you can see, we all know this, right? And then we have the constraints here where x is in between negative 100 to 100, then n is in between the full range of binary integers, and n is equal to integer and either that. So what I want to do, excuse the background noise, so what I want to do here is to, normally you want to go through the normal route of doing the multiplying this nth number of times, and that's good, only that it will exceed the time limit and it is very not efficient, and it will not pass some test cases. I already tried it before, it didn't pass the test cases. It passed 300, and out of 300 and I think 20 or something, it passed about 307 and right. So it wasn't efficient at all. It had a time limit. You write the correct algorithm, it's just going to exceed the time limit. So after a bit of research, I found out that in order to solve this question, you need to think about this in terms of binary, right? Go back to the binary format. And the first things, you need to understand certain binaries, which is that you want to use the power, right, and multiply and do some computation only when in the binary equivalent of this number you find one there, right? And that's the short version of it. You can do your own research at one, your own research. But I'm going to write the algorithm here, which you're going to see. And the first thing we are going to do is we'll have to initialize our variables, that is result. And there's also a trick here where you see they will give you they can give you the positive integer, the maximum of a positive integer, but when you go to the negative, right, you get to have a problem there where it becomes a problem. And I think, is it the opposite? Yeah, I think the maximum of a negative integer is greater. If you convert it to a positive, it's going to be greater, and you're going to have some problems. So the ideal solution, at least in this solution, the ideal approach is to convert this particular integer into a long. So we're going to have going to be that we're going to have long, we're going to have power, should just like power there, should be equal to n. Okay, and then we're going to have result, which is going to be double result to be equals to, we're going to initialize it to 1.0, and obviously that's because one always start at 1. Anything multiplied by itself by result will be 1. Normally we have to iterate and then we multiply the result by the value, and so in order to be efficient in doing so, we need to start the result at 1, so that 1, when you have say x to the 1, right, will be x times 1. So x to the 1 is x, and in order to replicate that, the result has to start at 1. You get, and it will continue like that. So if I'm explaining it well, if you have x to the 1, right, you have to say x, it will be x 1 times, right? So the answer of this will be x. Now, in order to replicate this, you have to loop, and in that loop, you have to multiply. Normally, if you look at the algorithm, you have to always multiply result by x. The problem is, if you start result at 0, then you're always going to stay at 0, because anything multiplied by 0 will be 0. So result, you can also start result at x, because it doesn't properly represent. You have to find a way to start like 1 or 2 after, and it becomes complicated. So that's why we initialize result to 0, because then when we go the first time, result is 1 times x will give you x, right? And our result, so it will be result equal to that, right? And now result will be now x, and then the next time will be result, which is x times the result times the x, which will now give you, say, x to the power 2, right? If we have x to the power 2 here, which will now give you like x times x, which now will give you x squared, right? And so on and so forth. So in order to do that, we need to initialize that. And the other thing we also need to do is check if this is a negative or a positive, because remember, power works different when it's a positive or a negative. And so if we have a negative, then we'll need whatever we're doing, we'll have to divide the result by 1, okay, to have the actual power. And in order to, while I'm going to the end and doing the division, we can just divide it up here, the initial result, by 1, and then whatever multiplication we're doing, we're always going to be multiplying by that fraction, which, as you know, gets smaller and smaller as long as you're multiplying a fraction by a whole number. And that's the idea. And we're going to do that. Does it get smaller and smaller? Yeah, as long as you multiply a fraction by itself. Yeah. So it gets smaller and smaller and smaller. So a fraction by another fraction doesn't have to be itself. And so one of the things we're going to do is check if power is negative, right? And we're going to do if power is greater, or if power is less than 0, right? What we want to do, so the variable we use is power, right? POW. If power is less than 0, what we want to do is, first things first, we want to put x is now equal to 1 on x, okay, and yeah, and then we're now going to iterate, right, for while n is greater than 0. Like I said, this is the iteration that I explained here. But within this iteration, we want to do a couple of things, right? One of the first things, if you look, if you research this problem, the most efficient way is that, you see, you're working with powers of So if you do, let's say you do 2 to the 3, or say 2 to the, what is it? 2 to the 4th, okay. Essentially, you have to do or let's say 2 to the 3rd. I think one of the examples I saw was like 2 to the 13th, right? It's it's, let's say you have something like 2 to the 1, 2 to the 1, right? And then you have 2 to the 2, okay? You have like 2 to the 3, right? And we have 2 to the 4, okay? And we can just continue all of that. So forgive me for making this a bit longer, but what I want to explain you see in a minute. You have 2 to the 5, 2 to the 6, 2 to the 7, and 2 to the 8, right? And then you can have down here 2 to the 9, 2 to the 10, 2 to the 11, 2 to the 12, and then of course 2 to the 13 itself. Now this, you can definitely look at this. You can write this again as you can write this as 2 to the 4, 2 to the 2 all together squared. Okay, and you can write this as 2 to the 4 all together squared, and right, and so you realize that you can start here, and this will be your and then of course you have to do the 13th below. Let's just put it below here so that we have that. Okay, and because you can write all of these, you can write this. There is a, if you go to the, if you use a binary form, I know that I'm not explaining it really well. I understand it, it's just difficult for me to explain. If from the binary perspective, right, you can represent 13, which of course it's 13 is, I think it's 1 1 0 1. That's 1 2 0. That's 4, and then that is 1 plus 2, 1 2 4, and that is 8. 4 plus 8 12. 4 plus 8 12 plus 1 13. Yes, so that is the binary representative of that. And it so just it doesn't so just happen that I think it was noticed that the ones correspond. If you do the iteration properly, you can do a multiplication. You can how do you call this thing? When you find, you can pick these values, right, and then I think multiply the base. I've forgotten how you do it, but where is it? I think yeah, I think this is it, something like that, something associated. Yes, so this is the research I did. You can do this, okay. You can have the res and you do the base, and essentially if you use it, uses the binary version of it. So it says initial, no, that's not exponential by squaring. The shortcut significantly reduce the number of multiplications, blah blah blah, which is 7 times. No, that's not what I'm looking for. How it works, example. To compute, we first express 9 in its binary. So we express the power to its binary form, and then initialize the result variable, say res equals to 1, right? Of course, as a result, that will really initialize, and the base is equals to x will really initialize the base, and then we iterate through the binary digits. So we are using the binary. So in our algorithm, though we're not going to like go binary, right? We're going to use like numbers. We're going to say numbers there, but you know our algorithm is going to take into account that we're doing like the binary. We're playing with the binaries of each digit, and iterate through the binary digits of the exponent from most significant bits to least significant bit, performing 2 steps at each stage, right? If the current bit is 1, multiply the result by. So exactly what I'm saying, that if you get 1, you multiply the result. So in our case, we'll start here at 1, we'll multiply the result, right? So you see, if the current bit is 1, multiply the result by the current base, right? And then square the base regardless of the bit value, it doesn't matter. So at the end of the day, you're going to have the result. So when you do the research and you understand it, it's a bit tricky. What the algorithm you get is you have to check if the first thing you check is if it is odd, if the power is odd, right? And because when they say the current bit is 1, you can also look like if it is odd, because if you have an odd, right, the last bit is always going, like the last bit will be 1. Okay, where is it? Yeah, so the last bit will be 1, and that's the same thing with the 9. All right, so you're going to start with the odd, and the last bit here at 9 will be 1. Okay, and then we're going to skip this 2. We are not going to do this first one for the next 2, and we're only going to do it for the last one, but we're going to do the second one regardless of the bits, and that's what we're simply going to do here. It's same logic. I know I'm butchering the explanation. There are probably better videos, but I just wanted to show you what I found and what I understood about it and how I solved the questions. And so we have, if the last bit, so we have to check last bit is 1, or better still, check if power is odd. And there is a way to do this, and which is the binary equivalent of checking if power is odd. Of course, in this case, because we did the okay, so if power is equals to this, so we can also, here we're supposed to make sure that minus equal to power minus equals to, no, is it, okay, it was just like minus power. We want like power is equals to 0 minus power, but it's the same like we do minus power here, right? And that gives our power to be minus. It's just a statement, and here our power is always going to be positive. So in this case, you can always do, you can also like just check like if power modulus 2 is greater than 0, right? Then we do a computation here, right? We add, oh yeah, multiply result slash base. Is it base? What's the name they give it? Oh, result by the current base, multiply result by the base, right? And of course, the base is always x, okay? And this is good, right? This is really good. But when you're dealing with, like I said, it's more of a binary thing. And I think if you do like you remove this here, when then power becomes negative, this becomes really wrong. And so most of the time, they always use like a safe way of doing this, and that allows them to work in the binary, and that allows them to manipulate, to take into account the binary form of the numbers, right? And this is what we're going to do. And I also found out today about this particular method, which was good. It was a good learning stuff. And I also found out that it's used a lot in lower level codes to make it to be more efficient. Because it computes the binary form, which of course, as you know, machines love the binary form. And the way you do that is power and, right, power and 1. So basically you're checking if the last bit is a 1, right, is equal to 1. So if power 1 is equal to 1, so that's what you're doing. So this checks, check last bit is 1, or check if power is, yeah, so this check if last bit is 1, or check, or basically you can also say that check if it is odd, because in this particular case it always tends it means the same thing, right? So and you would have to do result times equal to x, okay? And then once you do that, like, you have to now do the second square the current base, right? Base times base regardless of the value. And so we have to do x is equals to x, right? And now, because we have done this, we need to divide this. Now remember, we are skipping, we don't have to do we need to make sure that we don't have to iterate all through. We are only concerned just with this particular sections, and if you look at it, they kind of compress a whole lot of the other sections, right? Because they take into account all of that. And this next one is going to compress that. I know I'm not explaining it well again, but that's the idea. And in order to only focus on this and this and this, or at least if you go to the binary format, in order to I don't know if they explained it here, but what we are supposed to do here is, at the end of the day, we are supposed to divide this particular power, okay? So essentially this gets to the next, this gets to the next I don't know, the next power that we're interested in. It's like the next value, or the next bit. Let's say the next bit, right? Right, yes, I think that's the right way of saying it. This particular statement allows us to get to the next bit, and that's, it will be power. So the idea is to divide. Power is equals to power, right, divided by 2, okay? But again, like I said, when you're working for this particular algorithm, they prefer to take into account the bits, right, the binary format of the numbers. And so there is another way of doing this. I think it is power is equals to power. I think it's, if I'm not mistaken, it should be greater than 1. Yeah. Is it? I don't. Like I said, I forgot. These things are kind of. Is it greater than 1? Yeah. Anyway, we'll check it out. If I'm wrong, we'll check it out. But this like I think it says it goes to the next bit. It gets you to the next bit, because if we're working with the, so it will, for the next round, it will take this, right, which I think it will come here and do that. So get you to this particular value, and then for the next round you are going to have something like that, and so on. So it works from left to right and keep give you the next value. And so when you come here, the next value, when it checks here, you realize that it's not equals to 1, it's equals to 0. So it's going to skip this one and it's going to come and it's going to do that again. So it's like move to the next bit essentially. And you can do this by also dividing it by 2. And then we can just return results here. And I think that's how I solved it. Okay, so it's again, as you can see, it's not supposed to be power, it's supposed to be do I have it right? Time exceeded. Okay. I am missing something. Oh, what am I doing? Okay, so I'm using n here, so it's supposed to be power. Yeah. There we go. As you can see, it passes all the test cases. There are also some test cases that like I said, I previously failed some stuff. Like this one was what happens when you use the. Okay, this is like an overflow. For example, like the NA, this overflows the NA, and that's why we're using the long, because when you have the negative here, right? So when you put it, the negative integer goes here, but when we convert it to a positive integer, this is beyond a positive integer, and so it mixes up. It just kills the algorithm, and you know it does it's just wrong. It just produces wrong values, and that's why we don't do that. And when you get around this by using the longer multiplication, the longer power method, it time exceeds, right? It exceeds the time, and so. But this particular case makes the job really efficient and it's good. And it was really a good learning experience for me to research this particular question and actually get finding the solution to it, which was good. And not just finding the solution, understanding the solution and actually solving it now with you guys, gives me more understanding of it. As you can see, I wasn't pretty good about the articulation of my understanding, but the more I speak, the more I find the words, and like I said, I'm even better than when I started this video. So if we attempt to submit, it should pass, and it will pass with the first. Yeah, and so we have like 100%, 100% of time, and which was good. And also just to show you that I wasn't lying, you can see I already tried a lot of times. You can see a lot of time exceed, and I think this was the last one that I showed you. And if you look at the solution, it's a long division method, and it was not the best. I tried to write out the problem so I should find a solution. And why this solution is correct, right? As you can see, it's correct, but it hits the time limit. And so fundamentally, not fundamentally, in this particular case, it is wrong. Okay, if we had infinite processing power and space and all that, then this would be good. But this particular solution, I mean, that's 2 billion iterations, and that's a lot, a whole lot. But in this case, it's reduced. This particular thing is reduced to like 30 or so, right? So, which was really fun. And then, like I said, I researched it and I solved it, right? As you can see here. Then now I have just cleaned it out and I did it again. So This is not like me trying to say that, okay, no, this is my first time of solving these videos. Like I said, this is me just trying to make sure that what I understand, I try to pass it down. Maybe someone is going to learn one or two things from my struggles, right? So this was a good experience. It was a nice one, and thank you guys for watching. If you enjoyed this video, please give it a thumbs up. Comment your approach below. Comment what you've tried. Comment the errors you face. Comment whether or not you appreciate the videos or questions you have concerning the videos or other videos or other questions concerning solving LeetCode questions. I will be pleased to join you guys in the comments to talk about this. You can also follow me on my socials in the link in the description of this video, and connect with me on LinkedIn, and we're going to discuss on different things that you have to do. Right. So share the video if you like it, subscribe to the channel, and click the notification bell to get updates and alerts when I upload new content. I have some other good series coming up, architectural series and some other tutorials on Java, object-oriented programming, and some very interesting other content. So thank you guys for watching, and until next time, Happy New Year, and stay blessed. Bye.